Hey everybody, it's time for week 4, day 2. All right, so today we're going to talk about Isaac Newton a little bit. Isaac Newton, of course, the father of modern physics. Uh, what a quinky dink here. When Isaac Newton was in graduate school, the plague came through Europe. He was in Cambridge, and he and school was closed for 18 months because of the bubonic plague. 18 months, and now they call this the golden year, but it wasn't really a year. It was a year and a half. But during this time, Isaac Newton helped develop calculus. He also did the laws of motion. He also figured out optics, and that's with lenses and all that, the whole physics behind that. And then, of course, he discovered the universal law of gravitation. Right, so that's quite a break. So remember, don't limit yourself. Come back after this is over and have a few different branches of science developed, and it'll all be good. All right, well, let's get started on this. Let me erase that out of the way. Okay, well, first of all, this is Isaac Newton's universal law of gravity, and it's very similar to Coulomb's law, which we looked at in electricity. It's the one with the charges, remember that? So Q1, that was a charge, times Q2. Now, there could be positive and negative gravity. It's going to be masses. They have to be positive. Over the distance between them squared is equal to the force of electricity. Remember, we talked about K. K was that constant that was going to make it into a usable unit. In this case, it made it into newtons, which was named after Isaac Newton. So let's look at gravity. Oh my gosh, it looks just the same, right? Except we have masses, the masses of the two objects. So we can only focus on two objects at a time using this equation, but you know what, that's more than enough. And so we have the two objects and then the distance between them, and that equals the force in newtons. And here we have it again, another constant that's going to change into usable units. In our case, we're going to change it into newtons, because it is physics and we are studying newtons. And so we'll use G as a conversion into newtons. All right. So we did a bunch of things with that equation already. Remember, we talked about the distance between them. If it was twice the distance, that distance is squared, it'd be 1/4 of the force. Right, and if we doubled one of the masses, it'd be 2 times 1 over 1 squared. It'd be twice the force. And so we talked about that kind of stuff already. And you guys had it then, and I'm sure that you'll be fine with that. Okay, so let's look at our things. Now, the constant G, here's the number that we need for the equations. 6.67 times 10 to the negative 11th Newton meters squared over kilograms squared. And that is, again, just going to factor label those units. Oops, wrong one. That is just going to factor label those units for us and put it into a usable unit, which in this case is the Newton. Okay. All right, now discovering this unit, I mean, Newton had figured out this stuff about gravity, and they say the old story was he got hit in the head by an apple and boom, he discovered gravity. Well, that is not exactly true. Newton's own account says he was watching apples in the tree. He was watching an apple fall, and at the same time he could see the moon up in the distance. You know, one of those days, kind of like yesterday when the moon was visible, and he could also see the apple And it's one of those things where the apple's a lot closer, and so the apple looks about the same size as that moon. And then a wind blew or a breeze blew, something happened, and the apple poop, fell out of the sky. Well, out of the tree. And at that point, he asked himself, does the same gravity that affects that apple affect our moon? And that led him to the whole trying to calculate and figure out how gravity works. All right. Do you have any questions about that? I mean, there's tons of stuff about it on the internet. You can always look at that. You can always look at that kind of thing. There's movies about it. All right. Let's move on. Okay, so now Newton discovers this relationship between the moon and gravity and the apple and the gravity of Earth. And he comes up with that equation. And, they still needed to measure it. They didn't know exactly how strong it was. And so a guy named Cavendish comes up with this experiment. Now, here's a picture. And so we have a little mass that's like on a baton. You see that? There's a mass here. And it has two sides, so there's a mass on both sides. This doubles the strength of it, right? Two masses. And so let's just look at one side first. And so he has one mass, and then he has a giant cannonball, right? And the little baton with the masses on the end is hanging from a string that has a mirror on it. And they shoot a laser beam on that mirror, and it bounces back. And then he slowly rolls the big mass towards it. Well, it doesn't roll. It's on a little pivot. Now, both masses are attached to here. So he puts this mass closer and closer. And then he finds that the other mass is attracted to it. It actually moves. And then from the elasticity of that string, that twisting, he calculated the force that was caused by the mass. Now, that's just talking about one side. Now, of course, what happened was there's two masses, two sides of the baton. So the force was actually doubled when it turned it. So he just calculated using the masses, as double the masses. And that's how they came up with the constant G. They used that to figure out how strong gravity really was. I hope that makes sense. Okay. So now we were talking about Kepler in the last section, and we're talking about Newton. So what we're going to do, like we do in physics so often, is we take two equations talking about the similar type thing. This is the force of gravity. The other one is the forces that are moving planets around, and we combine them into one equation. And so using Kepler and Newton together, we come up with a way to calculate the period of an orbit. This is around the sun, and when we do this, it is it's so if we find something that is circling our sun, like an asteroid or another object, we can calculate how long it will take to get around. Or even our satellites, our man-made satellites. Okay, we're going to move on past that. All right, now, Newton. Newton uses a thought experiment. All the great scientists use thought experiments. Newton did this, Einstein did this, Galileo did this. It's like one of the main jumps from just being a normal science student and thinking about things and doing experiments between these great geniuses. What they do is they do an experiment in their head and still keep all the controls and all that idea and be fair and safe and imagine what's going to happen. And so Newton uses a cannon on top of a mountain. And he says, if I shoot this cannon, it'll follow that projectile motion, boom, and hit the earth. It's the highest mountain on Earth, by the way. And he said, if I shoot it a little bit faster, it'll go farther. And if I shoot it fast enough, theoretically, that curve of the projectile will follow the curve of the Earth, and the object will go completely around the Earth. And that is the basis of satellite motion. You know, how do we put these satellites up in orbit? We launch these satellites up in orbit, and then we push them fast enough that they are now going to follow that projectile motion around the Earth, and their curve is going to follow the curve of the Earth, and they're never going to hit the Earth. Now, sometimes these satellites, they slow down, or the old space, they called it Space Lab, right? It was out of commission for a long time, and it was just in outer space orbiting, and it started slowing down. I don't know if it got hit, I don't remember. And as they start to slow down, then they start to spiral. And whoosh, eventually things that are in orbit, if they do slow down or they're not going fast enough to stay in orbit, they will spiral and crash into the Earth. Most of the time things burn up, though, right? The friction in the atmosphere is enough to cause them to burn up. Okay, here's another weird term that we talk about, and that is weight, right? We know weight. We've done this all year. W equals mg, right? Well, we have a term we also call weightlessness, which you would think, oh yeah, that's when there's no mass or there's no gravity. Neither of those are true. There's always mass on these objects. There's always gravity, some kind of gravity affecting them. What we call zero G's, or weightlessness, is when both objects are falling at the same rate or acceleration. And here's our examples. Let's first look at the elevator. We might have seen this in the elevator section, right? If you're in the elevator, you weigh a certain amount. If you accelerate down, then the floor is moving away from you, and so what happens? You became lighter. If the elevator accelerates upward, that pushes the floor against you even more, and you become heavier. And if we cut the string all together, the elevator and you are both falling at the same rate, or you're accelerating towards the Earth at the same rate. At that time, you cannot push on the scales, and you are weightless. And so when you see on TV they're doing zero gravity experiments, look there, guys. Good example. Do your homework. All right. And so as you're doing these things, this is called the Vomit Comet, by the way, and it's a plane. One of my friends actually wrote on this. And this plane follows that path, that a real steep drop. It just drops right off, right towards the Earth, and then it cuts back up. And then for that split time, they are accelerating in the plane the same as gravity, and they are weightless for a little bit. And then they fly back up, and they do it over and over again, and just to get ready to either, in his case, he worked for a company out of Cleveland that he was an engineer there, and they worked with NASA a lot. And I don't know, he volunteered as a guinea pig in one of these experiments and got to ride on it. And his whole goal was not to throw up. And he said he was not successful in that goal. All right, here's another picture, and this is the same thing. They're doing the same thing now. They're showing that they're weightless. And again, when the people are pictures of people in the space shuttle or in the space station, and they're floating around, remember, they are still in the gravitational field of the Earth. The Earth is pulling on them and the ship at the same rate, and it seems like they are floating, but in real life, they're falling along with the ship. Oh, by the way, the space station went over the other night, about 2 days ago, and there's a an app, you can track the space station and you can see it go across the sky. And it's really bright because it's pretty big. So you check that next time I see it's going to come through again and it's visible, I'll make sure that I send out a remind so we can all see it. All right. Now, the speed of an orbiting satellite. Speaking of the space station, right? With using that same equation resolved, you can solve for velocity also. So if you know the height that object is above the Earth. Now we say above the Earth, but really we're talking about to the center of mass. I should have done a blue Earth, right? And so you have the Earth, and you have a satellite that is orbiting it. All right, now, when we measure that distance, we always go to the center of gravity. So when they say the distance between, we're talking about the distance between the center of gravity, not to the surface. So keep that in account when we get to doing different problems and different things, that you are not actually going to surface, but from center of gravity to center of gravity. All right, let's move on. Okay, let's look at problem 12. All right. Suppose that the satellite in example problem 2 is moving to an orbit that is 24 kilometers larger in radius than the previous orbit. What would be the speed? Is this faster or slower than the previous speed? Okay, so we're going to try to solve for the speed. And so we're trying to solve for the speed. That's this equation right here. Velocity is the speed. So v equals the square root of g times the mass of the Earth divided by that radius in between, right? Okay, so what I did is I wrote down the previous problems, the practice problems given. So let's look at that and see if we can adjust these. So the radius of the Earth is still the same, right? The mass of the Earth is still the same. G is still the same. The only difference is our height above the Earth, right? It's going to be 24 kilometers larger. 24 kilometers larger means 24000 meters, right? All I did is took 24 kilometers. For every 1 kilometer, that's 1,000 meters. And 24,000 meters. Okay, and that would be, since this is in scientific notation, let's just change this over. This would be 2, 2, 5, and this is going to go 5 more spaces. 1, 2, 3, 4, 5. So we're going to need 3 more zeros on that. Plus 2, 4, 1, 2, 3. Get out the handy dandy calculator here. You know, we could probably do this in our heads if we wanted to, but we're not going to do that. So we have 225000 plus 24000 equals, the new height above the Earth is going to be 249,000 meters. Okay, now we need to add that to the radius of the Earth. So our total R, our R above the Earth, our satellite is orbiting above the center of gravity, will be the addition of those two. So plus 6.6 0.38 EE6 equals, or R equals 6,629,123 meters. Okay, now we just have to plug that into the equation. So we have, let's rewrite it over here. 6.67 times 10 to the negative 11th times the mass of Earth, 5.97 times 10 to the 24th, divided by our new R, 6,629,000. Okay, punching this into your calculator. I mean, you guys, depends on what calculator you guys have. I'm using an iPhone right now, so I have to do my square root last. You guys with the new Texas Instruments calculators, you can put that in your normal way. Okay, now what I got for this. All right, last section. Gravitational field. Gravitational field, a force field, is an area that surrounds something that it doesn't have to touch it, that it can still affect it. Some force fields that we know about are like magnets, right? So if we have a magnetic force field, we have a bar magnet, north-south, and then it has these little lines of magnetism that go from point to point. And the magnetism, the force field is the strongest at the poles. That's where it can pick the most things up. And it's weaker around the outer edges out here. All right, but it can still attract things. Well, that's a magnetic force field. The gravitational force field is much easier. It just goes straight out from the object. So if we have the object in the middle, the gravitational force field is just lines of gravity force going straight out. All right. To figure out how much the gravity is, it all depends on, the main thing it depends on is, and I'm on this equation right here, I'm touching it with the eraser and it's just making it white, but is the distance away. So the closer you are, the greater the gravity. Closer to the center of the masses, the greater the gravity is, the greater the force is. Even on Earth, if you're on the top of the highest mountains, there's less gravity pulling on you than there is if you were at sea level. A measurable difference. I don't know exactly what the number is, but it is a difference. Okay. Mass. Newton goes on and talks about two different kinds of mass. Inertial mass, which means an object in motion stays in motion, an object at rest stays at rest, right? It's the mass that resists changing its motion. And that's what we've been using all year long with our F equals ma equation. Let me go to a different color, right? F equals ma, that mass is inertial mass. And the greater force we apply to the mass, the greater the acceleration. Newton also says that there's a gravitational mass, and that is the mass that's pulled by gravity or causes gravity. And then Newton goes on to say that both of those masses are equivalent or the same. And so I think Newton's trying to say there that there's only one real kind of mass, but it acts in two different ways. That's pretty much it. Done with Newton. Let's talk about Einstein real quick. Einstein's theory of gravity was a little different. Instead of talking about a force pulling on stuff, he talked about a curvature of space. Now, if you look on the notes on the Google, they'll be live and these GIFs move. And just like if you drop the quarter in that little yellow thing at Walmart, and it spins down the vortex, right? That's how Einstein says gravity is. He says that these big curves in space cause objects to follow that curve. In class, we would have done an experiment like the little GIF here on the side that I'm writing on. But since we're not in class, you'll have to look at that GIF. I hope that helps. Now, down here are some review problems. Again, I said I would post some answers. And so I'll put some answers down here, some number answers, but you have to show your work. All right, so thank you, and we'll go on to a new chapter next week. This will be week 4 homework, and you can do all those things that we had in red. Thank you very much. Have a great day.